Hello everyone, my name is Dr. Jean-Marc Grazioli, but my students call me Dr. G, as I'm an assistant professor of computational chemistry at San Jose State University. So as I mentioned in the beginning of the video, I'm a computational chemist. So my students and I do research using computational chemistry. So essentially we use computers to understand chemistry better. And this could, of course, mean a lot of things. So let me give you one example of a molecular dynamics simulation. So with a molecular dynamics simulation, I want to try and understand better how a molecule moves. And this is really important. So for example, protein molecules in your body, right? The proteins are doing most of the work. And if we want to understand the way that they move, we can start out with a structure that has been determined by an experiment, right? So maybe X-ray crystallography, NMR spectroscopy, something like that, right? So somebody can give us a structure that they've measured experimentally and they know, okay, this is one static structure that we know the protein likes to be in this configuration, but we know that the protein's not, completely rigid, right? It moves. So what we can do is we start at that point and then we can simulate that protein interacting with water and see how it sort of behaves in solution rather than in, say, for example, a crystal structure. So how does that work? Well, basically, the simulation software is simulating laws of physics. So if you've ever played any sort of video game where the character's running around, jumping up and down, maybe throwing something, things are bouncing, things are moving in a very sort of natural physical way, then you've experienced a physics engine, right? That's part of a video game development is physics engine development. But it doesn't have to be a video game, right? We can do it for research purposes as well, for simulating molecules. And so it's the same idea, right? That's one of the main things that physics is all about, is finding the math that describes reality. And then once you have it into a mathematical form, then you can put it into a computer simulation and write a code that represents the math. So for example, if you see a protein molecule jiggling around in water, then what's going on there is that if you think about the physics that's going on, right? Those atoms have a given mass with some momentum in some direction, right? But they're getting pulled on by a bond, and the bond is acting kind of like a spring that then pulls it back, right? This is what's happening in a molecular dynamics simulation. And this is one of the many tools we use in my group. So we'll use more traditional molecular dynamics simulations, like what's typically done with proteins. We use network statistical simulations to look at a larger scale. So in that case, instead of individual atoms running into each other and bouncing around, these are entire protein molecules running into each other and sticking together and moving around. And we have some research in that area that's relevant to protein aggregation diseases. For example, Alzheimer's disease, where amyloid fibrils form. Huntington's disease is another example. And then we have other simulations that we run in the group where we get maybe more precise. Maybe, we don't just care about where the atoms are, but we want to know where the electron density is as well. So there's another project in my group where we're interested in trying to understand the photodissociation of a pollutant in the atmosphere, a molecule that it breaks apart and causes havoc in the ozone layer, right? And so basically, if we want to try and understand that, we need to know not only where the atoms are, but we want to understand how the electron density is moving around, and we want a really precise description of the dynamics that are dictated by that. And we also use a great deal of machine learning. And in a nutshell, machine learning is where you construct a general model in a computer of something you're trying to make predictions on. Like, let's say pictures of cats versus dogs, right? Instead of trying to start from the beginning and say, okay, let's see here. The program should measure the distance between the eyes. It should measure the length of the snout, the color of the nose. I don't know, all sorts of things like that, right? You could try to come up with all the rules ahead of time that the computer program should follow in classifying pictures as being either a dog or a cat. Or you could say, let me construct a general model and give it a big data set of pictures of dogs and cats. So maybe the computer has the answers and basically tweaks all the parameters in the model until it starts getting the training data correct. And then you can give it data it's never seen before and say, hey, is this a dog or a cat? And if you've done a good job training the model, it'll be able to give you the answer on a picture it's never seen before. So that's what machine learning is. And obviously we don't study pictures of dogs and cats. We use it in chemistry, but I wanted to mention that as well. That's another thing that we do in my research group. So if working in my research group sounds like something you'd be interested in doing, please go to my website. I'll link it in the description. Please read a little bit more about the work that I do, and feel free to email me through my San Jose State email address, which is given on my website. And I look forward to hearing from you, and I wish you all the best in your academic careers and beyond.